That's interesting. Who was here in 2022 from the people that, one hand? Wow, that's great. 2022 was the first time I participated of Spring I/O as an attendee, and kind of changed my life. Let me show you a photograph of that day. Like, this is me. No, this is me. Ah, okay, sorry. This is me here. Like, yeah. I cannot zoom in. Oh, I can. And I can prove this is me, because you can see that light spot here in the back of the head. I have this thing here. So yeah, this is me. And this is insane, because I work with this guy now. And he's the reason I kind of started sharing knowledge and creating YouTube videos, and the reason why I work for Redis now. So I work with him, so it's pretty cool. And the reason why I'm telling you that is that today you are in the audience, but tomorrow you may be on the stage as well. You know, it's all about sharing knowledge. It's not about who's speaking, but it's about actually the audience and the content that we're sharing. So just an interesting stuff. It was about a library that Redis implements that is called Redis Om Spring. Om stands for Object Mapping. And Brian, the guy who was speaking, is the one that started implementing it. And now I also contribute to it, and Ricardo here, who also works with us, also contributes to it. And basically, in his talk, he was telling us about everything that Redis is besides being a cache. And it kind of blew my mind. I didn't know all of the capabilities he had. So I decided to learn in public, and I started making like YouTube videos about it until like it caught the attention of people at Redis, my manager, and he decided to send me a message and say, hey, you're doing this for free. Would you like to get paid to do so? Basically, so it worked out. Just an interesting story before we get started. So, like, when you're connecting to Redis from Spring, you have two options. You have Spring Data Redis, and you have Redis on Spring. But the thing is that Redis evolved so much in the past 15 years and got a lot of new capabilities. Spring Data Redis didn't really keep up. We're actually going after that now. I have two colleagues from Redis that works now on Spring Data Redis and the integrations. I think they're not in the room right now. But because of that, we created Redis on Spring, which is built on top of Spring Data Redis itself and extends the capabilities of Redis. Let's wait one more minute. People coming in. Is there anybody that lives in the Netherlands here? Few hands. In Utrecht? Yeah? Okay. All right. That's really cool. On Monday, I'm going to be speaking at the Java user group in Utrecht about agentic memory. So if you're around and want to show up, that would be a pleasure. Yeah, cool. All right, I think it's time. Can get started. So my name is Raphael De Leo. I work for Redis. I don't really introduce myself because I don't think my talks are about me. I think they're about you and the content that I'm delivering, right? And today I'm here to talk about how we can reduce LLM calls with vector search. But before we actually get started, let me ask you, who still uses Stack Overflow? A lot of hands. That's so cool. Okay, this guy here was like, yeah, more or less. A lot of people fall back. Yeah, exactly. So you guys are part of the resistance, right? You're really resisting, like making it alive. That's really cool. A nice thing that Stack Overflow still does every year is that developer survey where they ask thousands of developers about the tools that they're using, the technology that they're interested in, so they can create this kind of understanding of what's trending in the communities or not, right? Last year, they also started asking questions about agentic applications. And one of the questions was, what is the data storage tool that people use the most when building agentic applications, right? And if you look at that, not really to our surprise, let me figure it out. Okay, Redis was selected as the most popular data storage tool for agentic applications. And I told you that it's not to my surprise, because we've actually been working hard to that. Who has used Redis before? Who knows Redis? A lot of hands. Who knew Redis was more than a cache? Not so many people, right? And since 2022, even before ChatGPT was released, Redis was already a vector database, right? So if you've built real-time applications in the past 15 years, chances are high that Redis was part of your stack. And now if you're building agentic applications, we want to get Redis and establish Redis as part of your agentic infrastructure as well. So we're very honored that the community is already looking at us like that. Enough of chit-chatting. Let's actually start contextualizing into what we're going to be talking about today. An interesting thing that happens every time a new model comes out, either from Anthropic, OpenAI, Google, DeepMind, whatever, is that people always come out, a few people in the community, of course, to say that now RAG is dead, right? RAG has been killed, I don't know, a couple of times already, 10, 20 times. Every time a new model comes out, people say that it's dead. And it's always with a different rationale behind it, right? A different reasoning behind it. So you can see that the first time I delivered this talk was in September of the last year. And at the time, GPT-5 had just been released. And the reasoning here is that even though the context window isn't super high, you can see we're here of 256,000 tokens that you can input into GPT-5. What they were reasoning about, what they were saying is that right now, the precision of the model when using the whole context window of 256,000 tokens was of 90%. So you could use this whole window and still be precise, still find the information you had inputted into the model, right? But there's still another problem here, and actually two problems. The first one is that you can see that in 256,000 tokens, you can stuff something like one book of Harry Potter, which is like about this thickness, if you have read it, The Order of Phoenix. But guys, if you've worked at banks or insurance companies or bureaucratic companies, you know that this is nothing, right? If you have an insurance policy, you know that this is nothing, right? And it's not only that information that you need to stuff in the prompt, but also previous messages, tools that your model should call, and other information that is important for the task in hand for the model to solve as well, right? Last month, GPT 5.4 was released, and again, the same message started coming out, right? Are there any Brazilians in the room? No Brazilians? All right, so this guy is a very big name in Brazil. He also said that RAG is dead now with GPT 5.4. So GPT 5.4 has a context window that is 4 times larger than GPT 5 at 1 million tokens, right? But you can see that the precision actually decreased. So when you're using up to 256,000 tokens, you have a precision of 80% compared to 90% of GPT-5. And now that you can use up to 1 million tokens, after you start using more than 500,000 tokens, your precision drops to 36%. So it's not really precise. You can use this whole context window, but your agent is not going to be effective with the information that it has in hand at the time. And not only that, if you looked at the price before, it was $1.25 for every million input tokens and $10 for every million output tokens. And now with GPT 5.4, the price has increased, right? So you're paying more with every model that is released. And what we want in enterprise systems, we want to pay less, right? That's what you want to do. You don't want to, I mean, if we're building an agent for enterprise systems, distributed agents that needs to serve hundreds or thousands of users, you want to pay less. You want to make less requests and be more cost effective, right? And that's exactly what we're going to be talking about today. Okay, so we're going to be seeing how we can make our agents more cost effective and more performant as well by looking at 3 different patterns and 3 different challenges as well. So we're going to be talking about semantic classification, semantic tool calling, and semantic caching. All of those are built on top of vector search, right? Who has done anything with vector search before? A few hands. Who has implemented RAG applications or RAG pipelines? Not many hands. Who has implemented like an agentic application with a loop, tools? All right, just 3 or 4 hands. So let me just recap vector search very quickly so everybody's kind of on the same page, because this is basically the technology that is behind everything you're going to be looking at today. All right, so roughly speaking, and in a very, not very, but kind of wrong way, we can say that a vector is a point in a multidimensional vector space. All right? So in this case, we can think of 5 points, A, B, C, D, and E. And what you can do with these points of 2 dimensions here is actually place them in a coordinate system of 2 axes. So X and Y. And we can look at them here, and we can, just by looking at them, tell how close they are to each other in this multidimensional vector space. We're talking about only 2 dimensions here. All right? And then, if you look at this specific point here, this specific vector, you can tell that this other one is actually the closest to it. Right? You can do that with your eyes, but we can also do that mathematically. And computers are really good at mathematical operations. So what computers can do is actually calculate what are the most proximate vectors to this one that we have in hand right here. And why is this important? Because back in 2012, researchers from Google DeepMind, they understood that they could extract meaning out of, or encode the meaning out of text into vectors like this. So you got unstructured data such as text or images, you ran them through an embedding model, and this embedding model, which is trained in a neural network, can extract a vector of hundreds of dimensions or thousands of dimensions, depending on the one that you're using, that is encoding the meaning, right? So that if you look at 2 strings like that, where you have, for example, what's the capital of Spain and which city is the capital of Spain, even though those are 2 different strings, mathematically, by looking at the vectors that represent both of these strings, we can see that they're semantically similar because they're also close to each other in this vector multidimensional space, right? Before I talk about it, so this is basically how vector search works and what it allows us to do. It allows us to see how similar 2 different strings are semantically speaking, and not only by exact keyword matching, all right? At Redis, we've been creating a lot of videos explaining this concept and other concepts as well, so I invite you all to check our YouTube channel later on and see videos that I have been making, Ricardo have been making as well, and other people have been making at Redis. Now that we're all kind of on the same page, let's talk about our first challenge of today, which is classifying text. Right? When you try to classify text, we can actually use an LLM to do so. So if we have a text such as every repeated LLM call is money on fire, Redis 8 semantic caching understands meaning, not just keys, and then a link, and you get this text and send it to an LLM alongside a question such as, is this about Redis? The LLM can output a structured output with a Boolean basically saying true or false, right? And this works really well. It can classify text fairly well, right? But the problem with this is that for every text that you're trying to classify, you're paying for that in terms of token, and it also taking time to process your request, right? So you're paying for tokens, and you're spending time doing so. So what is the alternative here? What can we do instead? We can use a vector database. So for using a vector database, there are 2 phases we have to go through. The first phase is the preparation phase, where you're going to prepare the data that is going to be stored inside of the vector database. And the second phase is the activation phase. Right? So what you want to do is, first of all, come up with couple hundreds, 200, 300 references of the type of text that you're trying to classify. So let's say that we're trying to classify posts on social media about artificial intelligence. So I need around 200, 300 references of posts like this. You can come up with those manually, or you can actually use an LLM to generically synthesize these references for you. So in the case that I'm going to show you today in the demo, I actually got a prompt like this, more complex than this one, but something like generate 100 social media posts about artificial intelligence in our case. I sent that to the LLM, and the LLM came up with the references for us. With those references in hand, what I want to do is run each one of them through an embedding model so that I can get the vector representation of those sentences and then store all of those vectors inside a vector database, which is going to be Redis in our case here today. So this is the preparation phase. Once you have all of these references and their respective vector representations loaded within the vector database, which is Redis, we can go to the activation phase. So at this point, what you want to do is you get the text that you actually want to classify, the same text we had seen before. We're also going to vectorize this text. We're going to pass it through an embedding model, so we get the vector representation of it. And then you're going to perform similarity search or vector search within the vector database, trying to find out what is the closest reference that we have created inside of Redis to the one that we have in hand right now, right? After that, we're going to look at the similarity score, so how close it is in this vector, multidimensional vector space. And if that's close enough, according to a threshold that we have set up before, we can confidently say that this text that we're trying to classify is about the topic that we're trying to classify it into or not. Right? Let's look at a demo of how we can do that. For the demo, we're going to use a library that we also developed that is called Redis VL, Redis Vector Library. For Java, in this case, it's also available in Python. And I prepared these Kotlin notebooks here for us to see how it actually works. So let me just prepare the infrastructure here. I'm going to start test containers. I'm going to start a Redis instance inside of our Docker. I'm going to create a Docker network for later. I'm going to start the container itself. I'm going to add the dependency to Redis VL. OK, and now we're going to talk about what we're actually going to do. So first of all, we need to set up an embedding model, a vectorizer. Right? In this case, you're going to use a sentence transformers one provided by Hugging Face, which is an open source one that can easily run locally, the all-mini LLM L6 v2. If I'm not mistaken, this one has kind of 384 dimensions. And then I can try to vectorize a sentence such as, what is the capital city of the Netherlands? Let's change this to Spain here. And let me play this. And you can see that this is the vector representation of this string right here, right? So we have a vectorizer in hand. Now that we do that, let's get all of these references that I have previously created, which is in this file, references.txt. Each line of this file is a different reference, all right? Let me show you these references that I have loaded into this variable here. So you can look at the first 10 references here that were generated for me. AI for beginners, what is ChatGPT, how LLMs work, and so on. But you have many more than that inside of that file, right? After that, we're going to create a route using Redis VL, right? So this route is going to be named artificial intelligence references. We're going to pass the references to it, and you're going to set a minimum threshold, all right? So 0 is the closest, and 1 is the most distant in that sense, so 0 to 1. I'm going to create this route, and now we're going to create a router. But before that, I'm going to set up the connection with Redis with Jettis here. Then I'm going to create the router itself using the semantic router abstraction that is provided by Redis VL. I'm going to give it a name, AI router. I'm going to give the connection to Redis. I'm going to give it the vectorizer that we set up before, and all of the routes that this router should be able to classify text into. All right? In this case, we have only one, which is the artificial intelligence route. After I do this, you can see that it takes a little while, about a couple seconds, took 3 seconds, and that's because it's going through all of the references, vectorizing these references, and storing them inside of Redis for us. And now that we've done that, we can actually try to match text. So if you get a text such as, Redis is a great tool for building applied AI systems because it works well as agent memory, I can call the router, the route function, send that query to it, and try to match something. So let's see if it works. And you can see that it worked. It matched the artificial intelligence references route with the similarity score of 0.58 right here. But if I say something like Flevoland is a nice place to visit, which is a place in the Netherlands, and if you live in the Netherlands, you know that it may be true, but maybe not. And I try to match this one. You can see that it didn't match any routes because we don't have any references within Redis related to Flevoland, right? So you can see that the classifier is working as intended in this case, but I want to show you before I continue what it looks like inside of Redis itself. So I'm going to start Redis Insight, which is our GUI for looking at what we have inside of Redis. Okay, hope it has started. Let me open this in localhost 5540. Okay. It didn't work. I think I already had another local. I will show you in the end Redis Insight and how the data looks like in Redis. Let's get back to the presentation now. Because we've got a lot of content to cover. So guys, one thing that you may think of is that the quality of your classifier is related to the quality of the references that you create. Right? So if the references that you create or that are generated for yourself are not kind of similar to the text that you're trying to classify, your classifier is not going to work very well. So what you can do instead is try a little bit more complex setup that we call classification self-improvement here. So what you're going to do is basically the same thing, but with every text that you positively classify, you add it back to your vector database as a new reference. So along the time, your classifier becomes more accurate because it's going to get more references that have been classified as positive in the past, right? But sometimes that's not enough. So another approach that you can take is a hybrid approach to improve accuracy. So in this case, you also want to add the positive classified text back into Redis as a new reference. But if something is classified as negative by the classifier, the semantic classifier itself, what you want to do is fall back into the LLM so that you let the LLM classify this as positive or negative. So check if it was a false negative or not. And then you want to get this text and also add it back to your vectorizer, your vector database as a new reference. Right? So that within time, your classifier becomes more accurate, and you depend less and less on the LLM. So in the beginning, you're going to depend more, but within time, you're going to depend every time less of your LLM with the hybrid approach. Right? Any questions so far about semantic classification? No? All right, so let's continue, and let's talk about now the second challenge, which is calling the right tools. Right? So if you've built agentic applications, let's say using Spring AI or another framework such as LangChain4j, or even in another ecosystem such as LangGraph for Python or for Node.js, you know that you can call tools using this framework, basically. Right? So you can tell Spring AI, for example, that you have this number of methods that are tools. You can give that to the framework, and then the framework is going to pass that information to the LLM, and the LLM is going to give a response back, basically saying, okay, based on these tools, I want you to call that specific tool right there. The problem with that is that you need to have more calls between your framework and the LLM for that to work. Because the LLM is not calling the tools itself. It's just generating text, and this text is telling the framework to call the tool. The framework is going to call the tool. It's going to get the response from the tool. It's going to stuff into the prompt and make a new call to the LLM. Right? So ultimately, you're going to be paying more. You're going to increase the token consumption, and you're also going to spend more time for every tool that you call. So what you can do instead, you can use a vector database using vector search one more time. So you're going to see that all of these patterns that you're going to implement, they're all built on top of vector search. Right? In this case, what you're going to do is you're also going to come up with references, such as what's the weather like, will it rain today, hello, what can you do, hello, how can you help me? And all of these references, they're going to reference a different tool, right? Or the same tool. So the first two, for example, are referencing get weather default city. The two second ones are referencing the greeting and help tool. The third ones are referencing the new notifications tool, and so on, right? So that you can also get each of these references, vectorize them, store their vector representations within the vector database, so that when you get a new prompt, a new request later on, you can try to vectorize this, which is in this case, what are you capable of? You can get the vector representation of it, send your vector database, performing vector search or similarity search, finding out what is the closest reference you have inside of the vector database to it, and if it's similar enough, what you can do is call the tool proactively instead of getting the LLM to decide to call this tool for you. So you can say basically, okay, I know that the LLM is going to call this tool, I'm going to call it, and then I'm going to trigger the LLM, right? With the other tools as well that the LLM can call as a fallback if needed. Let's look at a demo of the recipe. There's going to be another application in the end. They're going to show you as well. So before I do this one, let me just tear down all of the containers here. I think I had already done it, probably. So tool calling, for all of these recipes, since they're intended for you to run them at home later on, they all have the same beginning, starting the Redis Docker container. Okay, what is codex? All right, let's add the Redis VL dependency. Let's create the vectorizer. It's going to be the same thing. And now we're going to have 3 different routes instead of only one. So before we had the artificial intelligence route. Now we have the get weather route, the FAQ route, and the notifications route. And you can see that the references for each one of those are pretty shorter here. So for the first one, get weather route, we have 4 different references. What's the weather like? What's the weather today? Will it rain today? Is it raining? For the FAQ one, you have what can you do? What are you capable of? What problems can you solve? How can you help me? And the notifications one, you have other 3 references here. So you're going to create the router the same way we did before, but this time we're going to have 3 routes instead of only one inside of the router. Did I run this one? I hadn't. Let me run this again. Okay, so our router is created. So now we can try to match these strings right here. So we have like, do I have new notifications? If I try to match this one, it worked well. It routed to the notifications route. So I can call this tool proactively instead of expecting my LLM to ask me to call it, right? Or the second one, will it be sunny today? And you can see that it matched the get weather route correctly with a similarity score of 0.24. And as you remember, we don't have references that look exactly like those in the references that we vectorized and created inside of Redis, right? So those are semantically similar. Or for example, what tasks are you capable of? And it matched the FAQ route. And finally, Stampot is the most nutritious meal. And if you run this one, you see that it didn't match anything because, well, we don't have any references to Stampot or food inside of our references inside of Redis, right? Let me tear down this part as well. So this is semantic tool calling. But again, when you're talking about vector search, accuracy is always a big deal, right? So the first time I was playing with semantic tool calling was last year during Kotlin Conf. And one of the things I realized for the agent that I was building was that people don't always phrase stuff very precisely, right? So you can see that somebody could write something like, hey, I had a bad day yesterday, the weather was terrible, and I crashed my bike onto a tree. Anyway, will it also rain today? So you see that the person wrote a lot of stuff, but they're just asking if it's going to rain that day or not. And the problem with that is that we don't have any reference within our vector database that is similar enough to all of the stacks. If we try to classify it, it's not going to be similar enough to any of them, and then we're not going to call the getWeather tool because, well, it's not going to classify it properly, right? So what you can do instead, which I was playing with last year, was basically tool calling chunking, where you get the prompt and you chunk it based on the punctuation of your prompt, your request, right? So that you can get different sentences or sub-sentences such as, hey, I had a bad day yesterday, the weather was terrible, and I crashed my bike onto a tree, and anyway, will it also rain today? And you can try to classify each one of them separately. And vector search is very fast. It takes like a couple milliseconds to do so, so you don't have to worry about classifying a lot of them. You're not going to create a lot of tail latency amplification there. But if you do that, in the end, the chances that you match the actual reference that you were intending to match in the vector database is much higher, and you're going to call the tool as you expected. Right? So that's just another way of improving that. And this is tool calling. Do you have any questions about tool calling so far?
No, I have one. So when
yeah.
you ask a question and you do get a positive hit, do you also include it as a reference every time, or do you sort of do some kind of step where you identify some good candidate references to index in your vector database as well?
That's a good question. I haven't tried to do like self-improvement with this, but this is something that we can always explore. So if we even benchmark this, I would really appreciate it, or somebody else would be great. Even like Redis VL, Redis Vector Library, these are open source libraries, and if you guys want to like contribute to them, we're always open to that. Even though we have agentic coding nowadays, we still need a lot of people to help us implementing these things. All right, so challenge number 3, caching responses. I think this is the most interesting one in that sense and the most useful one. Because another thing that I forgot to tell you is that these patterns, they're very useful, but maybe they're not applicable to all of the agentic applications. So they're not silver bullets, but they're patterns that are important for you to have in your tool belt so that you can identify when they can be applied and they can help you create agents that are more cost-effective and performant as well, right? And this one, which is the caching responses, the semantic caching one, is the one that is probably the most applicable across agents, all right? So basically, the idea here is that with every request that you make to your LLM, you're going to pay for tokens and you're going to wait for the time it takes to process, right? And the thing is, sometimes people ask questions that are very similar to each other, or even the same person asks the same questions multiple times. So I can ask something like, what is the capital of Spain, for example, and this is going to go through the pipeline and go through the RAG pipeline and get the documents from the database and then trigger the LLM, and it's going to take 5-10 seconds to do so, right? So that I can go back there afterwards, or somebody else can go in the same agent and ask a similar question, just for all of this process to run again, and you pay for the tokens, and you wait for the time as well, right? So what you could do instead is what you call semantic caching. So what you want to do is, you have, for example, the user prompt, and then you vectorize this user prompt like before, and then you check your cache, your vector database, to see if any responses, any requests like this had been triggered to your LLM before, right? And if you have anything in your database that is similar enough to this, you can return that response right away, while if you don't, you can trigger your whole pipeline. And then you trigger a whole pipeline, you generate the response, you generate the vector representation of the request, and you store the vector representation of the request in Redis alongside the response, so that the next time somebody asks a similar question, you get it directly from the cache instead of going through the whole process once again.
Can I ask something about that? So,
yeah.
When you ask a question,
yeah.
you cache the vector, right? Or you do a cache lookup with the
yeah.
vector of the question?
You cache the vector alongside the response.
Yes. So when you ask, or when someone else asks a very similar but slightly differently phrased question, the vector might be similar but not an exact hit.
Yes.
So does it just return the closest hit as a cache result?
Yes. So just like all the other examples that I shared, you need to set up a threshold, right? So how similar it should be for it to trigger the cache. So if it's not similar enough, then you say, okay, this is not similar enough. This is a different request, basically, right? Let's look at. I have two demos for this one. So the first one is the pre-generated semantic caching here, and this is another idea that you don't need to wait for people to make requests for you to cache them. Since you know your business and you know what people are going to ask you, you can proactively generate the answers for most of the questions they're going to ask and store the vector representations of these questions alongside the responses to them in Redis beforehand. So if people ask something about your business that you know that is frequently asked, you can get it back from the cache right away instead of making them wait very long for that information, right? And that's exactly what I'm going to show you right now. So this is running. Okay, let me start test containers. Let me start Redis, the network that we need, the container itself. Add the dependency. So now, that's what I wanted to talk about. I got a brochure of a Chevrolet car from the United States, and I basically generated a lot of question and answers from this brochure. And let's say that I work for this company, and I'm creating a chatbot that's going to allow people to ask questions about this car. I know what questions they may ask, so I can pre-generate these questions alongside the answers for it, right? And that's exactly what I did. So I have this JSON with all of these pairs of questions and answers that I'm going to load into memory here. So you can see that I loaded 346 FAQs from the file. Then I'm going to create the embedding model one more time. And now we're going to use a different abstraction from Redis VL, which is called semantic cache instead of semantic router, right? And here we're going to give a name to it. We're going to set up a distance threshold, so how similar it should be. a TTL, a time to live, an expiration inside of Redis of how long this information should be valid. So depending on what you're caching, let's say that you're caching stock prices, right? This should be cached for 1 minute, for example. But let's say that they're caching fundamentals from stocks. This can be stored for longer, for example, for a quarter or for a year, depending on your business, right? In this case, we're going to store this information for 360 seconds. I'm also going to give the connection to Redis and the vectorizer. Let me create this. Now that the semantic caching is set up, I'm going to go through each of those FAQ pairs that we created before, and I'm going to store them in the cache using the store function, where the first one is the request itself and the second one is the response. So I'm pre-generating all of that inside of Redis so that I can ask something like, what models of Chevy Colorado are available? And you can see that it matched this sentence here, this question here, which is, what are the available models of the Colorado? It's slightly different, but it still means the same thing. And you can see that we got the response right from Redis. And you cannot see it here. Let me run this again. It took like 92 milliseconds here, but we also take into consideration in these milliseconds the time that it takes to create the embedding, right? And the distance was of 0.18 in this case. Or you can ask something like, is an entertainment system included with the car? And if I ask this one, you can see that it was slightly different. So we have what entertainment system is included in the vehicle. You got the response right away. You don't have to go through your LLM. You don't have to trigger your RAG pipeline. You can get that information right from Redis in a much faster way. Or if you ask something like, does the car drive on the water? You can see that it didn't match anything in the cache. You have a cache miss here. So in this case, you're going to trigger your regular pipeline. You're going to do your regular RAG thing. You're going to trigger the LLM, and then you're going to pay for tokens. And maybe you can even store the response into Redis in the semantic cache as well. So that when somebody asks a similar question in the future, they don't have to go through this one more time. Sorry. I wanted to show you this as well. Because, like all applications nowadays, they kind of have an agentic chatbot included in it, right? And last year, I got solar panels installed in my house, and they also have an application that I can check insights from the solar panels. And you can see that in this application, they actually suggest questions that I can make to their agentic chatbot. And these questions, they're always the same, and those are questions that they know the answer for, because they're suggesting that I ask them, right? And let's see what happens when I click in one of them. So I recorded the screen of my phone, and you can see that I clicked in one of them. It triggered their agentic chatbot, and it took 9 seconds to process the request. So it took 9 seconds to generate the response for an answer for a question that they already know I'm going to ask and that they're suggesting that I ask. So it's kind of a bad UX in that sense. Not criticizing the app. The app works really well. I'm very satisfied with the company and everything else. But that specific part could be improved, right? If they had something like pre-generated semantic caching implemented in their application. So instead of waiting 9 seconds, we could have waited just like 400 milliseconds. Yes?
So I did notice, like, it stated, like, your specific amount, like, some user data is involved, right? So
Yes.
can you still apply semantic caching if, let's say, the user data is differing from user A and
Yeah,
user B?
yeah. That's actually a great question. He's asking if when you're dealing with like multiple users, and these users are asking questions, and you're storing these questions in the cache, if we can actually separate these questions by user ID, for example. And this is something we can do. So in the semantic caching, you can also store metadata alongside, and part of this metadata can be a user ID. So if in the future somebody asks a question that has been asked before, you can also filter by user ID and not get like PII leaked from one user to another. That's a great question. We also offer what we call lane cache, which is a managed version of semantic caching on Redis Cloud, that you don't need to worry about implementing all of the infrastructure yourself. You can just trigger it using like REST APIs and store things in the cache or retrieve things from the cache with that. All right, and there's something else I wanted to talk about, because at Redis, we're also performing a lot of research, and part of this research is related to semantic caching as well. So our AI engineering team came up with this paper last year, and also an embedding model that we trained ourselves, which is called Lane Cache Embed V2. I think we're in V3 or V4. already. But what we realized as well is that most embedding models, if you had questions that were very similar, such as what is the capital of Spain and what is not the capital of Spain, your embedding model would still trigger those as the same question, even though they're the opposite ones, right? So the reason why we created this embedding model is that it's actually a specialist in detecting sentences that are negating each other or other use cases like this, where questions are very similar, but they actually mean the opposite thing. So if you're implementing a semantic caching, like using a link cache embed model would be the ideal way to go with. All right, and now let's talk about integrating with Spring AI. Who has used Spring AI before? Just a few hands. Who was at Christian's talk yesterday where he talked about Spring AI, Spring Advisors? Okay, a few hands as well. Christian is the head of Spring AI. He's speaking in the next room or something like that part about advanced agentic patterns right now. But in Spring AI, we have the concept of advisors as well, which is basically interceptors, right? So you can create multiple advisors. For example, in this case, we have advisor number 1 and advisor n, for example. And with every prompt that you send to your agentic application, it's going to be intercepted. And these advisors are going to advise the prompt, do something with it. You can implement whatever you want. So it's going to intercept it. You can check a semantic cache. You can check a semantic guardrail that is based on classification, for example, right? You can even stuff things in the prompt, like long-term memories, so that when it hits the chat model, OpenAI, Amazon Bedrock, Gemini itself, right? You have this extra information in it. And after you get that response back from your model, it can be intercepted again so that you can get that information and do something else to it, such as storing in the semantic caching, or, for example, stuffing more information into it, right? So in our case here, what you're going to end up with is with 2 advisors, so such as the semantic guardrail advisor for the demo that I'm going to show you after that, and the semantic caching advisor. So when you receive a prompt, the first advisor, the semantic guardrail one, is going to check if this is allowed, considering the references we have created in our database. If it's allowed, it's going to trigger the second advisor that is going to check the cache and see if something has been processed that is similar to the request that is being made right now. And if there's no cache hit, it's going to trigger the chat model. Otherwise, we're just going to short circuit and return the information right back to the user from the cache, or saying that something is not allowed using our semantic classifier here, right? After that, the semantic caching advisor is going to be intercepted again if there is no cache hit and the chat model was triggered. And in this case, we're going to store that information in the cache. And we're also not going to do anything with the guardrail advisor because after we don't need to do anything, right? So that we can return the response back to the user afterwards. So this is a little bit of what the advisor would look like if you're implementing it with Spring AI. So they offer 2 classes, or 2 interfaces actually, the call advisor and the base advisor. And with those interfaces, you can, in the case of the call advisor, you can intercept the call itself, and the base advisor, you can set up an after, a before and after for that, so that this can be plugged into your chat client in Spring AI later on, right? So this is the example of the semantic guardrail. You can see that we're implementing the call advisor interface, and because of that, we need to also implement the advise call method. And in this call, you can see that what we're doing is we're using Redis VL, the examples that I showed you before, to try to match our semantic classifier and see if that text falls into one of the examples that I created that shouldn't be allowed to be processed. If it's not, as you can see in the match.isEmpty, it means that our request can go through and go to our chat model and pay for tokens and so on. Otherwise, we're going to respond with something that has been pre-generated by me, such as this type of requests are not allowed for this agent, for example. So it's pretty straightforward, which is the greatest thing of Spring AI. It's very easy to get it started with. Let me show you a demo of this working. So I have this stock analysis agent that I created for Java 1 2 weeks ago for a workshop that I delivered there. Let me zoom in a little bit. And this is a multi-agent application built on top of Spring AI. All right? So if I ask a question such as, tell me a joke about aliens. Let's see if it's running. So I created a semantic guardrail, which is a semantic classifier, and I added only 2 references to it. Jokes about aliens and corporate questions about agile, for example. So you can see that in this case, it didn't trigger the agent. It was blocked by the guardrail, right? If I run this again, it took a little bit longer, probably because I hadn't sent any requests. But you can see that it was much faster now with 598 milliseconds to return. So you can see that it didn't even trigger the LLM. We didn't pay for any tokens here, 0 tokens as well, and I was able to block this request. Or for example, if I say something like, tell me everything about Scrum, let's say. If I send this, you can see again that it was blocked by the guardrail, and this is not generated by the LLM. This is a pre-generated information that I created inside of the application itself if this was intercepted in this way. Right? But if I ask a question such as, what do the fundamentals for Apple look like? This is going to take a couple of seconds, because this is going to trigger multiple sub-agents. They're going to trigger third-party APIs, such as Stavely for searching, and market data for getting the price. And in this case, you can see that it went through the LLM. It took 13 seconds to generate this information, and I spent almost 400 tokens to do so. And if you look at the execution breakdown, you can see that 3 different sub-agents were called. So the coordinator one, the fundamentals one, and the synthesizer one. So what I can do now is, so the question that I asked was, what do the fundamentals for Apple look like? I could ask something like, what do the fundamentals for Apple look good? Let's see if this is similar enough according to my threshold. And it was. And you can see that in this case, it retrieved the information right from the cache, from the semantic caching, even though the question was different, right? It took only 345 milliseconds in comparison to the 13 seconds that it took before, and I spent basically nothing, right? 0 tokens to do so, and I got the same response because this response was cached in the semantic caching, right? So this is a demo. I'm going to have a link in the end for you to run that locally as well, if you want to play with that. And I still have 5 minutes, so before I finish, let me just talk a little bit more about optimizing accuracy, because before I told you that the quality of the references was important, but you also need to set a threshold of how similar should stuff be, right? And that's the tricky part, because it's a little bit heuristically that you find out. However, one of my colleagues, Robert Shelton, who is also an AI engineer at Redis, he came up with this retrieval optimizer. This is available on GitHub. This is open source. You can run it locally. And what you can do is provide a set of test data and also an example of your classifier. And this is going to run the tests for you and come up with the result in the end of how similar or what the threshold should be for your specific router or semantic caching, right? So you don't have to figure it out yourself. You can also use the tool that we provide ourselves, that is the retrieval optimizer. Not only for that, so you can see that we have the threshold optimization as one of the features, but for example, if you're building a RAG pipeline and you're trying to assess or evaluate different embedding models, for example, for your RAG application, we also have in this library ways of doing so without taking you a lot of time, just by relying on delivering a test data and also what the embedding models you want to test. Because this is a problem that many customers of ours were facing, so that's why he decided to streamline this. And finally, before we finalize, why Redis as a vector database? We have so many vector databases in the market today. Basically, every database became a vector database recently in the past few years, right? But Redis is all about speed, you know that, and we've been trying to stay. We already are, but we're working hard to stay as the fastest vector database out there. You can check the benchmarks we've been creating as well, but you can see that we are the fastest by large in comparison to other vector databases, at least the mainstream ones in the market today. So this is why Redis. And finally, so Lane Cache is our managed service for performing semantic caching, and we have access to how many tokens we have saved so far. So this is a new service. It went to production last year. We already have customers working with this, and you can see that in January alone, Linkcash saved their customers more than 5 billion tokens. And according to ChatGPT, this was a colleague of mine that ran this check, that's approximately 2 trees saved per day, and their goal this year is to save 1 million trees based on how much tokens we save as well. This is not very accurate. I mean, we don't have a lot of research behind it, but just something that I wanted to add as well by the end of the talk. Finally, my name is Raphael Delio. I work as a software engineer and AI engineer and also a developer advocate within Redis. In the QR code, you can find all of my socials. You can find the slides for this presentation. You can find the GitHub for the Kotlin recipes and also for the stock analysis agent, so you can run that locally. Part of my job is talking to developers. So if you guys have any questions and you want to connect on LinkedIn, you want to connect on Twitter or anywhere else, feel free to do so. Send me messages. I'm always happy to talk, chat, not only about Redis, but also about agentic applications in general. So if you have anything cool to share or just want to talk about in general, I'd love to talk to you. And guys, before we wrap up, do you mind if I take a selfie with you all so that my boss knows that I'm working? All right. Awesome. Thank you so much.